In this goal, we are going to be doing conversions. And one thing you need to know with doing conversions is you need to know how to calculate the formula weight or the formula mass. So on the periodic table, the mass given is the atomic weight or the average atomic mass. Those really mean the same thing. And when we put compounds together, so metals and nonmetals, and they're bonded together so that they're neutral, that formula that we write, it also has a mass. So we can write what's called the formula mass or the formula weight. So this is all the atoms in a compound that are added together. So let me give you an example. So this is calcium phosphate. Calcium has a +2 charge. The phosphate polyatomic ion has a -3 charge. So you put it together so it's neutral, Ca3, and then in parentheses PO4, 2. So to pick apart this, you have to figure out how many atoms there are. So in this first one, I have 3 atoms. So looking up the weight or the mass of just one calcium, I would get 40. So I multiply it by 3 and I'm going to get 120.24. Look at the phosphorus. I do have those parentheses. I can distribute the 2. So this would be a P2O8. We don't normally do that, but we're counting atoms, and I would have 2 phosphoruses. So that would be 61.94 is the total. And my oxygens, I would have 8 because 4 times 2 is 8. And 8 times 16 would give me 128. So to find the formula weight or the formula mass, I just add all those up, and I'm going to get 310.2 atomic mass units would be my unit, or you could use grams. So if you had 1 mole of it, which we're going to talk about next, we could also call it grams. Just like 1 dozen equals 12 of anything, in chemistry we have a unit that's kind of like a dozen. We call it the mole. And this mole is a very, very big number. It's 6.02 times 10 to the 23rd of anything. It's also known as Avogadro's number. Avogadro was a scientist that studied gases, and he looked at the ratio that the gases react together, and this number is attributed to him because of his work in chemistry. So a dozen means 12, a mole means 6.02 times 10 to the 23rd. And this is what it looks like. It's a huge number. And that's because when we are working with quantities of atoms or molecules, we need to have quite a big sample size so that we can see it, to work with it. And so this mole quantity is used to standardize everything. So I can compare a mole of water molecules to a mole of oxygen molecules to a mole of sodium chloride crystals. So just to recap, 1 mole of anything, in this case water, is equal to 6.02 times 10 to the 23rd molecules of water. 1 mole of lead atoms would be 6.02 times 10 to the 23rd atoms of lead. Well, here's the question. Do they have the same mass? Do they have the same number of grams? And the answer is no, they wouldn't. And that is because the lead atoms are so much bigger than a molecule of water. So the lead would be in the hundreds of grams, and a mole of molecules of water would only be 18 grams. So just like you can have a dozen cantaloupes or a dozen watermelons, the dozen watermelons would weigh more than the dozen cantaloupes. It's the same thing with chemistry. So even though you have the same number of molecules or the same number of atoms, they would still have different weights. This is called the mole triangle. This will help you with your conversions. You'll want to jot this down in your notes. These arrows mean equal signs. So I could have 6.02 times 10 to the 23rd of anything. That is equal to 1 mole, which is equal to the molar mass in grams. And I get this from the periodic table. Also, when we talk about gases, 1 mole is equal to 22.4 liters of gas at standard temperature and pressure, STP. And this is just a number that you have to memorize. And we are going to revisit this when we talk about gases. So the formula mass or the molar mass It can be measured in atomic mass units or in grams per mole. And again, you get this from the periodic table. Now, anytime I have 6.02 times 10 to the 23rd of anything, that could be atoms or molecules or formula units, that is equal to the masses that I can add up from the periodic table, or it's equal to 1 mole. So all of those mean the same thing. Why do we have to have moles? Because if we want to compare anything, they need to be in the same units. So 1 gram of lead and 1 gram of water, they are not equal. They're going to have different number of atoms and different number of molecules. And so we'll have a hard time comparing them. But I could compare 1 mole of lead with 1 mole of water, because then I would have equal number of atoms to molecules. So on the AP free response, converting something and telling how many moles it has is usually an easy way to get 1 point. So if you're ever having a hard time getting started, take your numbers that you have and convert them to moles, and you might get a point out of it. It also might jog your memory of what to do next. So when we're doing these conversions between moles and grams or Avogadro's number of anything, we want to start with the given number. We want to cancel the units diagonally, and we want to use conversion factors. Conversion factors mean that we have two things that are equal to each other, and we've put them on top of each other in a ratio. And because they're equal to each other, it's like multiplying the original number by 1. Then we want to multiply and divide and make sure our units cancel. This is where it's so important to write your unit every single time. So let's do a conversion with this first problem. It says convert 3 moles of ammonia, NH3, to grams of ammonia. And look, I'm given a conversion factor. So 1 mole of NH3 is equal to 17 grams. And this is determined from the periodic table. Nitrogen is about 14 grams. And each of the hydrogens is 1. And so when I add up all the molar masses or the formula weights on the periodic table, I'm going to get 17 grams. We start with the number they give us, which is 3 moles. I make sure that I write that down. And then I want to cancel out moles, so that goes down below. And I'm going to use this conversion factor right here. 1 mole is equal to 17 grams. My moles is going to cancel because one's on the top and one's on the bottom. And then I'm left to multiply and divide. So when I go across, I multiply. And when I go down, I divide. So I'm going to go 3 times 17 divided by 1. And when I do this, I get 51.0 grams of my ammonia. So again, these two things, 17 grams equal to 1 mole, is because they're equal to each other. That's a conversion factor. Putting them on top of each other just means I'm multiplying that original number by 1. So I'm not changing the quantity that I'm starting with. I'm just changing the units. And that's the whole purpose of these conversions, is to change your units. Let's try another problem. How many molecules of carbon dioxide are in 2 moles of carbon dioxide? So start with the number they give us. And I know I want to cancel out moles, so moles goes down here. And we want to change to molecules. Well, what do I know about moles and molecules? I know that 1 mole is equal to 6.02 times 10 to the 23rd molecules. So that number is going to go here, Avogadro's number. And down below I have 1. So when you're working with conversion factors, it's always going to be 1 mole is equal to something, either grams on the triangle or Avogadro's number. So notice that my moles cancels and I'm left with molecules, which is what I want my answer in. And then I just have to do my math. So I have 2 times 6.02 times 10 to the 23rd divided by 1. So when I do this, I get my answer. It is 1.20 times 10 to the 24th molecules. So molecules are not a mole and they're not a gram. And so therefore you have to use Avogadro's number. And notice I start with 3 sig figs. And so I want to have my answer have 3 sig figs. Let's do the next one. How many molecules are in 7.5 grams of methane? And I want to change to molecules. So I'm going to cancel grams and I'm going to change it to molecules. Molecules are not grams or moles. So that's Avogadro's number. That's the anything. And I have to figure out how many grams. How many grams are in my Avogadro's number worth of molecules? Well, look at my triangle. The molar mass from the periodic table is equal to 1 mole, which is equal to Avogadro's number. All those are equal to each other. And I'm really just working with these two, okay? So let's go ahead and figure out my grams. So carbon on the periodic table is 12. Hydrogen is 1, so 4 times 1. So that means the methane has to be 16 grams. And again, I get these numbers over here from the periodic table. So grams cancels, I'm left with molecules, which is what I want my answer in. And doing the math, I get 2.82 times 10 to the 23rd molecules. And it says how many atoms of hydrogen are that? So for this one, I know that there are 4 atoms hydrogen per 1 CH4 molecule. So really, all I have to do is multiply my number by 4. And when I multiply it out, I get 1.13 times 10 to the 24th atoms. All right, let's do one where we're using the gas conversion. So remember, 22.4 liters of gas at standard temperature and pressure. It has to be at standard temperature and pressure. Standard temperature is 0 degrees Celsius, and standard pressure is 1 atmosphere. So if you're not at that temperature or that pressure, you can't use the 22.4 liters. But this one is nitrogen gas at STP, and we have 9 grams of it. So using this conversion, I have grams here at the bottom I'm going to cancel out, and it wants liters, so 22.4 liters at STP. And to find the grams, I need to do the molar mass of nitrogen. So nitrogen is 14, I have 2 of them, so it's going to be 28. Grams will cancel, and I'm left with liters, and my final answer is 7.2 liters.